All right, so here I'm projecting one problem related to uh, critical radius of insulation. So we will read the problem here. A 5 millimeter diameter spherical ball at 50 degrees Celsius is covered by a 1 millimeter thick plastic insulation. K is given as 0.13 watt per meter Kelvin. The ball is exposed to a medium at 15 degrees Celsius with a combined convection and radiation heat transfer coefficient of 20 watts per meter square Kelvin. Determine if the plastic insulation on the ball will help or hurt the heat transfer from the ball. So here there is a spherical ball having a certain temperature and covering it with a plastic insulation. We are asked to find out whether will it increase the heat transfer or decrease the heat transfer, or will it remain indifferent? Does it matter or does it not matter? So a very simple problem, but gives you some insight. Can you hear me? Am I audible to you?
Yes, sir.
Or disconnected? So here we are. The ball is exposed to a medium of 15 degrees Celsius. So let us first uh, it's pretty simple diagram. It's only a sphere with some insulation cover over it. So this is having a diameter of 5 millimeter diameter, and the insulation thickness is 1 millimeter of the insulation is 0.1. All is exposed to a medium of 15 degrees Celsius. So T in degree, and the combined heat transfer coefficient, both radiation and convection heat transfer coefficient, is 20 watt per meter. This is the data given. Determine if the plastic insulation on the ball will help or hurt heat transfer from the. So basically, whether this putting an insulation on this, is it going to increase or decrease the heat transfer? So we have seen that if you remember this graph, critical insulation thickness, we have seen the total resistance, the resistance the thermal resistance on the y-axis and the thickness of insulation R minus Ri. So let us say center Ri, and this is so R minus Ri gives the insulation thickness. So if you see this, the resistivity or thermal resistance, the combined resistance due to conduction and convection will decrease first, and then so at this point where the resistance is minimum, this is called as the critical radius of insulation. So at this point, we say this is the critical radius of insulation. At this point, thermal resistance is minimum, so heat transfer is maximum. So any thickness, any insulation thickness to the left of this point will have a higher thermal resistance, and any insulation to the right of this point will also have higher thermal resistance. So maximum resistance will be here. So if you are on the left side, you can keep adding insulation, and then you will be able to increase the heat transfer because the resistance is decreasing. But after this point, if you add resistance, if you add the insulation thickness, you are only uh, increasing the thermal resistance and thereby hurting the heat transfer. So on the left hand side, by adding insulation, you are aiding the heat transfer, whereas on the right side, adding insulation will be hurting the heat transfer. So you have to check whether the given insulation is to the left or to the right, or whether the given insulation thickness is lesser than the critical insulation thickness or not. So for that, you need to calculate the critical insulation thickness. Now, we have we have derived an equation for the critical insulation thickness um, for a cylinder, and the similar procedure can be followed for the sphere also. Now, the critical radius of insulation for a sphere RC is given as 2K by H. Now, this is in page 57 of data book. 2K by H. K is the conductivity of the plastic material, of this insulation material. H is the heat transfer coefficient. So this is 2 multiplied by K is how much? 0.13 divided by H is 20. So this will give you 0.013 meters of the critical radius of insulation. Okay, so this is 13 millimeters radius of. That means you see our radius is here. 5 millimeters is the inner radius and 1 millimeter is thickness. That means currently this R is 6 millimeters. So what this one says is if you increase this insulation thickness to 13, this radius to 13 millimeters, you will have maximum amount of heat transfer. That means this insulation thickness can actually go up to here. Okay. So the critical radius of insulation is 13 millimeters, and what is the current radius of insulation? Okay, this is not 5. Okay, 5 is the diameter. So Ri is 5 by 2 is 2.5 millimeters. Current R is 1 millimeter. Therefore, presently R outer with the insulation is 2.5 plus 1 is equal to 3.5 millimeters. But our calculation of the critical radius of insulation says that it should be this value, that should be 13. That radius itself should be 13. So 13 minus 2.5. 13 minus 2.5 is 10.5. So it should be 10.5. So our current R outer is 3.5, but we can go up to 10.5. Therefore, 3.5 current radius 3.5 is less than 10.5. Therefore, we are on the left side. So this is 10.5. So this is our 3.5. So we are on the left hand side of this point. That means adding insulation will actually improve the heat transfer. Therefore, insulation will help heat transfer. That should be the answer. Okay, so for such problems, the first step is to calculate the critical radius of insulation and compare that with the current radius of insulation. So if we are depending on the position, if we are lesser than the critical radius of insulation, then we should add insulation, and if we are greater than the critical radius of insulation, we should remove insulation. So accordingly, you can decide whether the given radius of insulation will help or hurt the heat transfer. So this is a spherical geometry. For a cylindrical geometry, the formula is different. It's simply h by k. Sorry, k by h. This is for sphere. It is 2k by h. For a cylinder, it is k by h. And these formulas are given in the data book. Now moving on to the next problem. This problem is related to a concept called as the overall heat transfer coefficient. So what is this overall heat transfer coefficient? We have seen in one of the earlier slides. Heat transfer coefficient. Now you can see here in this heat transfer, we used to calculate heat transfer as the overall temperature difference divided by the resistance. Okay, the resistance in this, as per this figure, the resistance is made out of 5 components. The first one is related to convection resistance. Second one is the conduction resistance. Third one is also conduction. Fourth one also conduction. And fifth one is convection resistance. So there are all 5 resistances. So overall temperature difference divided by the total resistance will give the heat transfer. Now the same thing can be represented as a Q is equal to UA delta T, where delta T is the overall temperature difference, A is the area available for heat transfer, and U is the overall heat transfer coefficient. We are tempted to write this equation in the form of the Newton's law of cooling. In Newton's law of cooling, we used to write it as a Q is equal to HA delta T. So in place of H, we have written U, which takes care of the conduction components also. Conduction components and convection components, and if there is radiation components also. So it is a very convenient way of writing the equation for the total heat transfer in a system. So in such a case, if you can write this, you see here, this U is related to these terms using this equation. So if you equate this to this, you will get U as this one. So this is for a linear system. That means a plane wall. Similarly, if you are dealing with the cylindrical system, cylindrical pipes and so on, the equations will differ according to the geometry. So the current problem is related to pipes. So how to estimate this overall heat transfer coefficient? So just remember, overall heat transfer coefficient is only a fictitious concept where we will combine all the effects of conduction, convection, and radiation into this parameter called U. U is the overall heat transfer coefficient. Now, if you turn to page 164 in the data book, turn to page 164 in the data book, you will see that there are approximate overall heat transfer coefficients for preliminary estimates. So many a times we will have to start with an unknown value. So for that we will need to use a guess value, a good estimate. So for that we have a list here. So for different conditions we have the overall heat transfer coefficient. For example, the first one is the steam to water instantaneous heater. So that is 2300 to 3500 watts per meter square Kelvin. Steam to water storage tank heater, 1000 to 1800. So for different situations, you have these different values. And also in the next page, in page number 165, you have what is called as the fouling resistance. So what happens is whenever you are using a heat exchanger with water flowing through it for a long period of time, some scales form because of the deposits and the salts. It could be mud deposit or it could be the salt. Often you notice that when you are servicing your geyser in your bathroom, over a period of time, there will be some scale formation. Therefore, the, the time taken to produce hot water will keep on increasing. Then you will have to remove that scale. So that is called as a fouling. So that can happen in heat exchangers in industrial applications also. So that fouling will actually offer some resistance. So in this page 165, the table on top gives you different fouling resistances. Okay, but anyway, we will not consider fouling for this at this stage. We will see when we deal with the concepts of heat exchangers, which we'll look into in the last module, module number 7. But as of now, let us look at this problem because this problem deals with the overall heat transfer coefficient, and the equation for overall heat transfer coefficient in tubular sections is given in this particular page 165. Okay, we'll keep this page open and readily for reference. Now we'll read the problem. A hot fluid at an average temperature of 200 degrees Celsius flows through a plastic pipe of a 4 centimeter outer diameter and 3 centimeter inner diameter. The thermal conductivity of plastic is 0.5 watt per meter Kelvin, and the convection heat transfer coefficient at the inside is 300 watt per meter square Kelvin. The pipe is located in a room at 30 degrees Celsius, and the heat transfer coefficient at the outer surface is 10 watts per meter square Kelvin. Calculate the overall heat transfer coefficient and the heat loss per unit length of the pipe. So this is the problem. So a lot of data is given, so it's always convenient to present it using some pictorial diagram. So I'll draw a pipe. So this pipe has got some yes. Okay, so some fluid is flowing through this pipe. We are given the fluid temperature 200 degrees Celsius. We're also given the heat. In the inside is 300 watt HI. The plastic pipe of 4 centimeter outer diameter and 3 centimeter. T out is 4 centimeter. T inner is 3 centimeter. So using this, we can calculate the outer and inner radii. So outer radii is a centimeter. Inner radius is 1.5 centimeters. The thermal conductivity of plastic is 0.5. So K for this material, K is 0.5. Okay, and the pipe is located in a room at 300 degrees Celsius. So 30 degrees Celsius. 30 degrees Celsius. And the heat transfer coefficient at outer surface is 10 watts per meter square Kelvin. So you can see inside pipe, the fluid is 200 degrees Celsius and outside the fluid is 30 degrees Celsius. So obviously the heat transfer will be in this direction. So this is the direction of heat transfer. And you can see that the resistances available for transferring heat. Firstly, the internal convection, then the conduction resistance of the pipe wall, and also the convection resistance on the outside of the pipe. So these are the resistances which the system has to overcome before transferring the heat. We are to find out the overall heat transfer coefficient and the heat loss per unit length of the pipe. Unit length L is equal to 1 meter. Okay. So this is the problem. So we are asked to find what is U. Now, in the previous earlier slide, I showed you about overall heat transfer coefficient. There is only U. U is evaluated using some equation. Now, when we come to this cylindrical systems, this radial systems, you see there is a inside radius and there is outside radius. So, when at the inner radius there is a certain area and outer radius there is a certain area. What is that area? At the inner side, the area for available for heat transfer will be 2 pi r I multiplied by L. 2 pi r I is the inner radius. So 2 pi r I multiplied by L. And on the outside, you will have 2 pi r O multiplied by L. RO is the outer radius. Therefore, in this radial systems, you will, since there are two areas inside and outside, the overall heat transfer coefficients also will be different. You will have a outer heat transfer coefficient, outside overall heat transfer coefficient, and inside heat transfer coefficient. So these two values will be different because the areas are different. But ultimately, whether you calculate the heat transfer rate using this value or this value, the heat transferred must be the same, irrespective of which one you use. So I'll demonstrate that now. Now, if you turn to page 165 of the data book, you see at the bottom, you have expressions for overall heat transfer coefficients, U naught, UO and UI. UO stands for outer, I stands for inner, for tubular section. So first I will take up the first equation, which is U naught is equal to 1 by HO plus RFO plus R naught by K log of R naught by RI plus R naught by RI RFI plus R naught by RI 1 by HI. So HO is the outside heat transfer coefficient. HI is the inside heat transfer coefficient. The second term you see RFO is the fouling factor on the outside. Similarly, RFI is the fouling factor on the inside. So in our problem, the fouling factor is not given. That means this resistance due to the fouling factor, we can take it as 0. That means this term and this term will vanish. So what remains is 1 by H naught plus R naught by K plus R naught by RI 1 by HI. Okay. Now we'll start substituting the values. 1 by outside heat transfer coefficient is 10 plus R outer is 2 centimeters. Convert that to meters. 2 multiplied by 10 power minus 2 divided by K is 0.5 plus logarithm of RO by RI. RO is 2 and RI is 1.5. Now in this ratio, I am not converting this 2 centimeters and 1.5 centimeters to meters because this is a ratio, and if I convert the 10 power minus 2 in the numerator and 10 power minus 2 in the denominator will cancel off. So there's no point in doing it. But here I will have to do because this is an absolute value. It's not a ratio of radii. But here this is a ratio of radii, therefore there is no need to convert. But if you are not comfortable, then you rather convert it, but it will get cancelled and the result will still be the same. Plus this term RO by RI is 2 divided by 1.5 multiplied by 1 by HI is 300. So if you calculate this, you will get What's the value you're getting? Can somebody calculate this? Okay. See, I have made a mistake. This is not plus, this is a multiplication sign. So this is actually this one term. Now it can be done. U 1 by U naught is a 0.116. U outer is inverse of that, the 8.62 watt per meter square Kelvin. So you will have the same units as the overall heat transfer coefficient. Okay, so this is the overall heat transfer coefficient based on the outer diameter. So U naught implies the outer diameter. Okay, so now we will calculate the heat transfer. U naught A outer multiplied by delta T. So 8.62 multiplied by 2 pi multiplied by R outer is multiplied by length is 1, 2 pi R L multiplied by the temperature inside is 200, outside is 30. So this, if you calculate, one 184.05 watts. Okay. Now this is the heat transferred. This is the heat transferred, and we are not saying whether this is Q naught or Qi. Whether it is inner or outer, it should be the same. Now let us verify that by calculating the overall heat transfer coefficient based on the inner diameter. So I will take this problem a little bit forward. But as far as the answering the question is concerned, this is done. You can stop here actually. But we'll take it ahead and calculate, use the other formula to calculate. So if you look in the page number 165 of the data book, you will find this equation 1 by Ui is equal to 1 by Hi. The second term is the fouling factor, which we'll ignore as we did in the previous case. Then Ri by K log of R naught by Ri plus Ri by R naught divided by 1 by H naught. This is the equation for estimating the inside overall heat transfer coefficient. So this is 1 by plus Ri by K. So inner is 0.5 and logarithm of R out by R plus 2 by 1.5 multiplied by 1 by. Okay, so let's compute this. Okay, see there's a mistake here. Ri, what is inner diameter is 0.5 and outer diameter is 2. The radius is 2 plus this is 0.0869. So this will give ui as 11.5. Now see this overall outside heat transfer coefficient is 8.62. Outside overall heat transfer coefficient is 8.62, and inside overall heat transfer coefficient is 11.5. These two are different. But if you calculate Q based on the inner heat transfer coefficient, then this is ui ai multiplied by delta T. So this should be 11.5 multiplied by 2 pi Ri is 1.5 centimeters, 1.5 to 10 power minus 2 into L is 1 multiplied by overall temperature difference is 200 minus 30. Okay, so this is 184.1 watt. So you see these two values. Q, this Q calculated using the outside overall heat transfer coefficient is 184. Similarly, this Q calculated using inside heat transfer coefficient is same 184. So the overall heat transfer coefficient is a function of the radius, because in radial systems like cylinders and spheres, the area changes with radius. This does not happen with plain walls or slabs, where whatever may be the thickness, the area is still be the same. Therefore, overall coefficient will not change. There's no concept of inner radius and outer radius there. So, but in case of radial systems like cylinders, we have this inner and outer radius, and because of that, we have these issues. Okay. So this is what I wanted to demonstrate, the concept of in overall heat transfer coefficient. You have this outside overall heat transfer coefficient, inside heat transfer overall heat transfer coefficient, but the heat transferred per se will be the same for both. All right. So with that, I will end this particular module. And as I said, I will demonstrate. I will demonstrate the software that I was talking about. So I'll do that now. Are you able to see the screen of this interactive heat transfer software?
Yes, sir. Yes, sir.
Now, as I said in the last class, it's very convenient because many are very convenient to solve equations. Okay. Now I will take a simple equation and show how this particular software easily solves it. Did I solve some equations in the last class?
No, sir.
Maybe I did. Okay, fine, no problem. I will solve it. I have a book in my hand, a book on uh, what is that? Numerical methods, something called as a numerical methods. Okay, now I'll simply take an equation of x minus equation. I want to find the value of x. So what I do is type the equation in this manner and say solve. So when you solve it, the initial guess, you see initial guess, the value of x, the software understands that the x is the unknown. So it will suggest one value, default value of the initial guess. By default, everything is 1. So by default, you should not take zeros, because whenever sometimes when the equation involves division with zero, you will have problems. So 1 is a safe guess, but again, it depends on the problem. So in this case, the software is suggesting to take 1 as the initial guess, but if you want, you can change it. I can make it 1.5 also. Then I'll say okay. It's solved already, and here in this browser called as the data browser, the value of x is given as 0.6071. Okay, so in that way you can solve it. I will delete the and now I'll take up another equation. I'll take a set of equations, two equations, x square minus 3xy Now, see, if I try to solve this equation, so you can see that there are two unknowns, x and y. If I try to solve this equation, it says number of unknowns exceeds the number of equations. So, software is capable of detecting and counting the number of unknowns and the number of equations. Only then it will attempt to solve. So, the next equation is y minus 2 multiplied by. So, these are the two equations. Now, these are two simultaneous equations. Solve them. I've solved it, and you have these answers here. So it has got quite power. So there is non-linearity, and it may take some time to solve manually, but it has automatically solved it. Okay. Now I'll take another equation. X is 1.393. So trigonometric, logarithmic, exponential, non-linear equations, all of this can be solved. Now, you may also want to sometimes bring in property values. For example, to solve some problems, you may need the property values. What we do as of now is to refer to the data book. And in the data book, the properties are listed. But here in this software, there are some properties listed already. So property values, if I say air. So air properties are listed here. And you have to, or you can give some ID to this. So air properties, let us see ID1. When I say ID1 and click here, see what is changing. Right now, you look at this row RHO is simply plain RHO only. When I type ID1 here and click here, RHO becomes RHO1. That is RHO1 is ID, because when you have multiple fluids, you may have to give RHO1, RHO2, and so on. So you can give the ID, and the temperature ID also you can give. Okay. Now you can bring all these property values into this workspace. I copied it. You can also drag and drop it like this. And you can close this. Okay, now you have the properties listed, and these are the equations which system uses to calculate. But this value of T1 is needed. So what you do is you at the beginning you can give what is T1. T1 Kelvin. Now I will solve this. When you solve it, you will see that all the property functions are red. Now you see in this space, all the property functions are available now. Okay, so now you can use these values to calculate, to do some calculations. For example, HA delta T or Q is equal to minus Ka dt by T. The K you can take from here. Okay, so this is one feature of this particular software. I will demonstrate one last thing. See, we have seen temperature profiles of slabs and cylinders, right? So I will take up one equation for a cylinder, temperature profile in a cylindrical shell. So this is in page 53 of your data book. Now in the software, you give this two slashes. It is only a comment. It will not be computed. It's not taken as a code. Okay. So I want to plot the temperature profile in a cylinder. For that, I need the inner temperature. I'll take inner temperature as 100, outer temperature as 50. Or at any location, let me take it as a 0.2. Now I want to calculate T. T is equal to minus A minus O multiplied by logarithm of R logarithm of R, not R, R1, R by R. Logarithm of R. Okay, so this equation will compute the temperature at a radial location of 0.2 at this value. Okay, let me solve it. So the temperature is 84.95. Now, what if you want to plot the temperature profile at every location? That means a curve. You want to get a curve of this temperature profile. So for that, what you can do is you click this this button called Explore, and it will ask which variable to explore. By default, it has taken it as R, so we'll keep it as R. Starting value 1, ending value 1, and step value 0.01. You can very well take it as 0.05 also, or 0.02 also, whichever. Okay, and this also you can change 1.5. You can change, but because our R2 is 1, so this is okay, and I'll press OK. That's it. Everything is calculated. Now I can plot. So X is R, which is the one which we swept, and Y is T, the temperature. You see here we have a temperature profile plotted. So in this way, you can also carry out parametric studies without actually calculating at each and every location. Okay. So in this way, you can use this particular software. So I will try to demonstrate for coming to whenever we deal with each and every module, I'll try to demonstrate this particular software. Maybe I'll solve 1 or 2 examples using this software so that you will be familiar with that. All right. Any questions?
No, sir.
So I'll stop here and take your attendance. Rutunidhi? Rutunidhi? Abhilash?
Present, sir.
And Cherian?
Present, sir.
Present, sir.
Dilip? Karth?
So Siddharth present, sir.
Ivatsan?
Present, sir.
Ian?
Present, sir.
Lanivel? Kant?
Present, sir.
Kalagan?
Present, sir.
Present, sir.
Vaibhav Karan?
Present, sir.
Amit Menon?
Present, sir.
Praveen?
Praveen, present, sir.
Sinju?
Adil, present, sir.
Chintan?
Present, sir. Chintan present, sir.
Hasan? Ayush Tripathi?
Present, sir.
Vardhan?
Present, sir.
Kumar?
Present. Hemant present, sir.
Present, sir.
Present, sir. Chandramani.
Present, sir. Shubh.
Sai Rohit,
Oh, present, sir.
P. Raman,
Present, sir.
Present, sir.
Deepesh,
Present, sir.
Sudh,
Yes, sir.
P. Kumaran,
Present, sir.
Krishna,
Present, sir.
Present, sir.
Yanti,
Present, sir.
Niket,
Present, sir.
Badri Narayanan, Vito,
Sir, Badri Narayan present, sir.
Sir,
Oh.
are we the present?
Ajit,
Present, sir.
Harish Raghav,
Present, sir.
Rahul,
Present, sir.
Firoz,
Firoz, present, sir.
Nihar present, sir.
Vishnu, present, sir.
Puri Shankar,
Present, sir.
Ishwar, A. Prakash,
Yes, sir.
Ja,
Present, sir.
Tim Kumar,
Yes, sir. So, present, sir. Charan.
Arun Ajay, Arnold Simon,
Present, sir.
Venkatesh,
Present, sir.
Priya, and Dev,
Present, sir.
and Dev,
Present, sir.
Arun,
Present, sir.
Rao, Ish Krishna,
Yes, sir.
Vedant Madhur,
Present, sir.
Anand,
Present, sir.
Rani, Kia Vasan,
Present, sir.
Laipriyan,
Present, sir.
Anand,
Present, sir.
Anish, present, sir.
Pushraj,
Present, sir.
Keshav Kumar,
Present, sir.
Ash Kumar,
Present, sir.
Tik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Varun Ahalyan, Sarvesh Krishnan,
Present, sir.
who is that? Sarvesh Krishnan,
Yes, sir. Sarvesh.
Mina,
Present, sir.
Effort
Chapin, present, sir.
Manoj,
Present, sir. Present, sir.
Present, sir. I missed it at first.
Sutunidhi,
Yes, sir. Mritunidhi, sir. And Mritunidhi.
So, Pranav Dilip present, sir.
Sir, Chaturvedi, present, sir.
welcome, welcome. Palanivel, Kritik Krishna, Chaturved,
Present, sir.
Hassan, Motishwar,
Present, sir.
Karan Ajay, Vamsi Krishna, Kunal Rao, Shivani,
Present, sir. Present, sir.
Varun Ahalyan, there are some messages. I will see. You can leave the class now.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Again on Monday, we'll meet on Monday. So, start a new module on Monday.